This was the first robotic arm I ever built. This was the BCN3D Moveo by BCN3D Technologies. It worked, but I knew that if I want to make it any more precise and any stronger, I need to develop my own robotic arm. And this is what this video will be about. So in this video I will show you how I'll be rebuilding the arm from the ground up, starting with the shoulder joint drive system. For this particular joint I decided to go with a cycloidal drive. So firstly we need to declare what even is a cycloidal drive. A cycloidal drive is basically a compact high torque gearbox. Instead of using normal gear teeth, it uses an eccentric disc that rolls inside a ring of pins, creating a huge gear reduction in a very small space. As you can see, the rest of the robotic arm has not been built yet. That is intentional. For this project I do not want to design the entire arm at once and then find out later that the basic joint design is not stiff or reliable enough. Instead I am developing it part by part, starting with the shoulder joint because this is one of the most critical sections of the whole arm, as it needs to bear the whole load of the arm. Right now I am working on the extension lever of the shoulder joint. This part will later become the mounting point for the elbow joint, so it needs to be stiff enough to handle the load without bending too much. It sounds simple, but in practice it affects almost everything. The geometry, the material choice, the wall thickness, the bearing placement, and even how the next joint will be attached, of course. So before I move on to the next full section of the robotic arm, I want to make sure that this joint actually makes mechanical sense, of course. What I have already built, however, is the custom PCB stepper motor controller that I will use to drive the shoulder joint. This board was designed in EasyEDA and manufactured by JLC PCB. It is built around an ESP32S3 as the main processor and a DRV8462 stepper motor driver for controlling the motor. This driver is especially useful for this project because it can handle high motor currents and a relatively high supply voltage, which is important for a joint that needs more torque than a small desktop robot arm. The PCB also includes a CAN bus interface, which will be useful later when multiple joints need to communicate with each other in more of a modular kind of setup. But before talking about the controller board in more detail, it makes sense to first look at how a stepper motor actually works. Because to design a proper stepper motor driver board, you first need to understand what is happening inside the motor, how the coils are energized, why current control matters, and what the electronics need to handle during a real operation scenario. To understand why I designed the controller board this way, it helps to look at what actually happens inside a stepper motor. A stepper motor does not rotate continuously like a normal DC motor. Instead, it moves in small defined steps. Inside the motor there are multiple coils arranged around the rotor. By powering these coils in a specific sequence, the controller creates a rotating magnetic field. The rotor then tries to align itself with that magnetic field. So when the controller energizes phase A, the rotor moves to one position. Then phase B is added and the magnetic field shifts slightly. After that, phase A changes direction, then phase B changes direction, and so on. Each change moves the magnetic field a little further around the motor, and the rotor follows it step by step. This is what makes stepper motors useful for robotics. You can control the position very precisely because every electrical step corresponds to a known mechanical movement. But there is one important detail. The driver cannot just switch voltage on and off randomly. The coils behave like inductors, so the current does not The driver has to control the current properly, otherwise the motor can lose torque, heat up too much, skip steps, or behave unpredictably. That is why the stepper driver is such an important part of the board. It handles the high current switching, current regulation, microstepping and protection features, while the ESP32S3 takes care of the control logic and communication. Now that we know how a stepper motor works, we can take a look at the PCB driver. The schematic design as well as the PCB layout and routing was done in a program called EasyEDA Pro. I can highly recommend this program because of its ease of use and beginner friendliness. As previously mentioned, at the core of the board is a DRV8462 stepper motor driver, which is made for driving bipolar stepper motors with high precision and high current capability. The board is intended for motors like NEMA 17 or NEMA 23, depending on the voltage, cooling and current settings. The driver supports step and direction control, which makes it compatible with common motion controllers, microcontrollers, and it also supports SPI communication, allowing the controller to read diagnostic data and configure internal driver settings in software. The board is designed to run from a higher motor supply voltage, typically in 24 to 36 volt range, which gives the stepper motor a better torque at higher speeds compared to lower voltage driver setups. For precision movement, the driver supports microstepping, meaning one full motor step can be divided into smaller steps. This makes the motion smoother, quieter and more accurate, which is especially useful for robotic joints, camera sliders, CNC style motion and automation systems. The board also includes important control and safety signals such as enable, ensleep, enfold and SPI status feedback. This allows the main controller to enable or disable the motor output, detect driver faults, and keep the system in a safe state during startup or debugging. So I've set the motor supply voltage to 24 volts DC with my lab bench power supply. I wrote a little bit of a test code for the ESP32 controller, and I've hooked up this little NEMA 17 stepper motor right here and just put some of those banana clips to better visualize the motion. Now if I press R in the control software, we should see the motor starting to turn. One direction, other direction, just switching up and forth and so on. And now when I press X, we should stop now. Perfect. Now that we have validated the PCB controller and it's clearly working, we need to think about what to do next. The next step in this project will be to build a suitable casing around the stepper motor controller with active cooling in fact, which I will publish on my GitHub. You can find the link for my GitHub in the video description down below. But also start designing the next part of the robotic arm. That will be a connecting lever between the shoulder joint and the next joint, which will be the elbow joint of course. If you don't want to miss out on that, I would suggest you follow me here on YouTube and also over on Instagram and TikTok and all the other platforms. I've linked those in the video descriptions. I would highly appreciate that. That would be really nice of you. If you enjoyed this video up to this point, you can leave a like and maybe type a comment on what I should do next or on what you would like to see next on this channel. And now for the final part of the video, a quick note to the sponsor of this video who made this project possible.
$85,000 prize pool. The Easy EDA 2026 Stars competition is now open worldwide. Material costs largely reimbursed. $100 JLC coupon for every qualified completed project. Top 28 engineers get invited to JLC Factory to see production up close. No pitch decks, no fluff, just working hardware. Submit your build now.